So homework questions. These were the assigned questions. Oops, you can't see that though. There you go. Do you want to just throw values out and see if other people agreed? Would that be okay?
Yeah.
All right, 34, what'd you get?
70.
Woo, that was cute. 70 what?
Joules.
Awesome. 35, what'd you get?
1100 joules.
1100 joules. We'll go back through them if we need to. 36?
That's why I didn't get it.
2 watts?
2 watts. 2 watts. I put the wrong
37?
140 watts.
140 watts? 43?
I don't know. Stronger.
Stronger?
Stronger. I said
No,
stronger.
I said stronger.
Okay, let's go through them. So for those of you that were not here, Gerald, so you want to write these down so you can write them down so you can do them and turn them in when we take the test so that you have credit for them. Anybody want to go through number 34? Are you okay with that one? Okay with that one, everybody? Yeah. You let me know. This is your game, not mine. Anybody want to go through 30? Yeah, go for it.
How do we know if the forces are parallel or not? Because I thought in 34 they were.
So that's a really good question. I would say that unless, like in these really simple ones, I would assume they are unless there's a picture or something that indicates that they're not. Does that make sense?
Because I was literally like, I don't know if these are.
Right, yeah. So it could be either 70 or it could be 0. Is that what you're saying?
Yeah. Because I said 0.
Gotcha. So like on number 34, work done when a 20 Newton force pushes a cart. So the force is pushing the cart is really what they're saying. Yeah. So I would multiply them. Does that make sense? So like,
I'll figure it out.
well, no, let's talk about it real quick. So if I have a cart, like my shopping cart, right? And I'm pushing it, I'm applying the force this way.
The gravity acting on the cart.
Gravity is acting on the cart. The normal force is acting on the cart too.
That's why I was so confused.
Oh, okay. So all the problems that we did last time were kind of special cases, right?
Okay.
So if we talk, this is 34. I'm just going to number it so that we've got it. So here's my shopping cart. Right? So and I'm applying a force. So I'm applying a force in this direction on cart. There is gravity, the force of the earth. On cart. And we got the floor on the cart, right? And we don't even know. There might be friction, right? We don't know for sure. But the thing that we want to know is how much work is done because of this force. Does that clarify it a little bit more? Okay. Yeah, so then we're just going to take that number, the 20 Newton force times the 3.5 meters. 35, work done in lifting a 500 Newton barbell 2.2 meters above the floor. And then we ignore the second question because we haven't really talked about that yet. Are we okay with that one, the 1100?
Yep.
Anybody want to go through that? Okay. 36 and 37, I forgot that I assigned these because I thought we were going to get to power yesterday. We didn't. So hopefully, oh wait, the equation's right there for you. How nice is that? So convenient. Calculate the watts of power expended when a force of 1 Newton moves a book 1 meter in 1 second. Okay. Were we okay with 2 watts? And then 37, were we okay with 140 watts? Yep. Sweet. Anybody not? Because sometimes I think people are like, I don't want to say anything. Speak up if you're not sure, because I'm here to help you. Go.
No, I gotta say this.
No, I'm talking to Promise.
For 37?
Yes.
Why am I laughing?
I don't know, because Abdul's ridiculous. That's why I would say yes.
I said that it was 0 watts for some reason because I think they were like,
I said 0 too.
yeah.
But I figured it was a force thing that I was confused.
The perpendicular versus
Because they're
parallel.
Perpendicular, not parallel.
Okay, so this one is the same. In fact, it's actually the exact same problem as 34, isn't it? It's the same numbers. It's just in a time of 0.5 seconds. So if you take this explanation of the way that the cart is being pushed, then does it make more sense? Or are you still not happy?
No, I guess it makes sense.
Okay. You don't have to hedge. Like if you're really not happy, then tell me. We okay though? Okay, yeah, cool. And we're gonna do some more power stuff today too, so that'll be good. And then 43, which requires more work, stretching a strong spring or a weak spring? Strong, right? Takes more force, right? More force over the same distance. More work. Sweet. Okay. Yesterday we worked out some problems. We did some calculations. I'm not going to make you do example 4 because I want to keep cruising. We're going to do some more calculations in a second. I do have a ranking task for you to do with work though. Oh, but you want something. What? It is, yeah, it's Mandarin Chinese.
What does that mean?
It says you should study Chinese.
Oh, yeah, that course you're offering?
Oh
Yeah.
my gosh, I really want to do that, but I'm taking Kirkwood.
You
Yeah,
totally
me
should. It's going to be so
too.
much fun. Oh my gosh.
We're taking Kirkwood. We can't even show up.
Yeah.
Oh,
I would take it.
Ooh, Hajila. You should go talk to your counselor and let them know that you're interested if they could do it at a different time. Because maybe they
Yeah,
can.
yeah,
I don't know.
yeah.
I don't know what the logistics are, but like it seems like if there's a lot of you that want to take it, but the early bird doesn't work, then maybe they can be creative. Yeah, they're gonna offer it next year. Super excited. Yeah. Anyway, that's what it says.
Yeah, I would definitely
My grandpa used to know how to speak Chinese fluently.
That's cool.
Because he was in the
All right, here we go, you guys. This one should not take you a super long time. Give it a shot. Take a look.
Should we just erase example 4?
I'm just not going to go through example 4 right now. We can come back to it. So at some point while you're processing this, write some things down. It can just be the answer. If you need to do a little working in your head, do that. I'll give you another minute and then we'll discuss this through tables. Are you ready to discuss? Give it a shot. Talk about it. Have a conversation. Everybody should be talking.
4 has to be in the same, parallel. Right. You can't have like C.
work or the floor.
Yeah, I work.
Rank the work done.
Yeah. and then we're-
Yeah, no, that's all like, is
Is this a trick question?
I have.
Well, I just feel like that was down.
Yeah,
So
so I'm down.
So that makes it zero.
C.
That's why
Oh.
so it's like C, D, and F. They're all 0 because D's are opposites and then the distance is up. It's like those are equal. Then D obviously, they just do mathematics. D is greater than A.
Yeah.
I don't, some of the stuff I just am not getting in my head, like I cannot.
That's why we're doing it, right?
Greater than
Like the parallel forces is not.
Draw pictures, baby.
Just greater than B and A, they're not, because B is I just signed a force equal A and D are 5 and E is 5.
All right. Are we at a point where you guys want to put answers on a board, or are you at a point where we need to talk about this a little bit?
And some
You want to do boards?
Bored, because then you should talk about it.
Okay. Well, I just didn't know how, like, if there was a level of confidence there that is ready to warrant boards, or if you were like super not sure what you were doing. All right, put something on that board. I'll get you a marker here in just a sec. Stay with me, my friend. Are you ready to show me your board yet? You guys are just speedy back there today. All right.
Yeah, that's what I've always wondered.
Because I was done with them with my children, and I could either throw them away or use them. Why we have baby washcloths as our erasers. Seemed like better for the environment to do that and then not buy new erasers. All right, let me see them. C. So B, I'm just writing down what we have. B greater than A, greater than C, equal to D, whoa, equal to E, equal to F. B, same. You have F less than or greater than E. Everything else is the same though, right? And you guys are all different over here. Okay, so we got B greater than A, which is equal to E.
See, that's what I originally had, but I changed it.
C equal to D equal to F. All right, I love it. Let's do it. Snooze. All right. This is what we got. I'm gonna make it a little smaller so I can see it all. Okay, there we go.
Wait, can I ask a question quick?
No, you may not. Of course you can ask a question.
Since the F
Yeah.
is going the other way.
Yeah.
This is why I changed my answer from theirs, but I was wondering, does that work if they're in opposite directions, or do they have to be going?
That's a really good question. What do you guys think? What was the conversation that went with that? Well, we haven't really talked about it yet.
They are still parallel. They're still parallel.
They are parallel, right?
But is that a different thing that we're doing there, or? What do you think? Because they're applying a force in the direction that the distance isn't even going, like the distance that they want to move in.
Right. So like when I first looked at this, I'm like, well, how could you even do that, right? But if it already had some sort of like speed, right? And then you're applying a force in this direction while it's moving this, you just slow it down, right? Mm-hmm. Your acceleration is going to be in the left, like going to the left as it moves that way. Do you think about kind of what we talked about work was? Do I have that? Where is that? Up here somewhere? Force applied force acting over a distance. Yeah. So with that picture, well, yeah, so they have to be parallel, right?
Oh yeah, definitely. So
is there a force that's being applied over a distance here?
Yeah.
There is. Is it, so generally when we think about doing work, we're like maybe speeding something up or something, right? Like we're trying to like get it to go. In this case, we're maybe not doing that. So this one is slowing down. The answer, and this would be something you're going to write down in your notes, right? If you have a force, if the force is, I'm going to say 180 degrees opposite, or in the opposite direction but parallel. You with me there? You understand what I'm saying? Okay. Then the work done is negative. The work done is negative. So negatives and positives matter again, kind of like they did with momentum. Okay. So that perhaps is going to affect answers. So I'm going to let you take that piece of information, run with it, adjust your answers if you need to, and then we'll regroup. Does that sound okay?
No.
Okay. We're learning through doing. It's a beautiful thing, you guys. So if you need to adjust your answer, do it. And if not, leave it there and hold it up so I can see it.
Yeah. Doesn't mean there's an opposite direction. So like, are we working on like magnitude?
It says rank the work done. It doesn't say rank the magnitude of the work done. Fair question. Did you guys catch that question in the subtlety that makes that? Okay. Rank the work done, not rank the magnitude of the work done.
That doesn't mean like less work. It just means different direction. Right? So that's just like
So which is more, 20 joules of work or negative 20 joules of work? Do you want it to be 20 degrees outside or negative 20 degrees outside? Are they the same thing?
bad.
You're still freezing.
Like the same temperature.
It's true. You could put it in Celsius and then it would be okay, right? Unless it's negative and then it would be unpleasant.
These are zero lessons.
I wish I thought in Celsius.
Yeah, I know.
I wish I need to train myself to think that way. I've tried before, like when I've been traveling, but it's hard to like get it out of your brain. All right, answers up. Let me see them. So we've got B, A, C, D, and then we're gonna change this to F, E. So we're changing it to this one. Sweet. Now we all agree?
Mhm.
You all agree, but I don't agree with you. That stinks. There's one thing that I disagree about. I agree with everything except one little bit. And it's the other subtlety that we haven't really talked about yet. Anybody? C. Yeah. So C is an arrow that can be broken down into two arrows. One that goes like this and one that goes like this. Are you with me there? Yeah. So does the force in C do some work? It does. How does the magnitude of the work in C compare to the work in A? It's less because this arrow is smaller than that arrow, right? I mean, we know that just because it's a right triangle. Is that okay? Yeah. So that would be another thing to write down. So we've got that one note about being 180 degrees. The other note that I would write down here, something that I would write down in my notes, would be that if the force is at an angle, take only the component or the piece that is parallel to the distance. Is that okay? We talked a little bit about components, I don't know, 3 or 4 months ago or something, okay? I don't know that I would ask you to actually do the math to do that, but you could. It would be a sine, cosine, tangent kind of game, right? You know an angle, you know a line, you can find the pieces. Okay? If I did that, it would not be on a test. Like I might do that on a problem set, but I wouldn't do that on a test because then on a problem set, you'd have time to ask and work and crunch it through. Okay? Questions on that? Go.
Basically, if it's not perpendicular to the distance, then there's always going to be like a component.
Exactly. That was a nice way to say that. If the force is not perpendicular to the distance, then there will be some component that is parallel.
So like if it's perpendicular, that means that the work is always gonna be 0.
Yeah.
And when it's not, okay, that's.
Yeah, yeah. I mean, if you think about that angle as changing, right? So when it's down here, it's all in the horizontal direction. Here it's getting less and less and less and less and less and less and less, and this is where it's 0 in that direction. Does that make sense?
Yeah.
Yeah, sine curves and those sorts of things. All right. Life is okay? Sweet. All right. Let's see. Okay, we're all right. I'm not going to get quite all the way through what I wanted to do today, but that's okay. Power. All right, let's talk about power. You already learned about power. It's really not hard, but let's write it down. Let's define it. Power is simply, okay, work over time. That's all it is. So it's how much work did you do, but also how fast did you do it, okay? So the faster you do it, the more power you have used or you have expelled, I guess is a verb that we use. Power is marked with the letter P, okay? Not to be confused with our other P, which is momentum, right? So P, capital P is power, little p, momentum. So I just got to keep that in our brains because it's a little bit funny. And P is equal to work. Actually, I'll just write it as W because we know that that's work, right? Over time. So I'll just write it over here this way. Power equals work over time. The one potentially confusing part of doing the power equation comes when you start looking at the units. And it's not really bad as long as you're paying attention. So the units for work are what? Joules. And the units for time are seconds. And the units for power is watts. I usually make a really good joke there. Watts? What? But I missed it. I missed my opportunity and now it's over. Darn it. All right. And so then if we write this out just as the units in letter form, then you get W is equal to J over S. Are you with me there? So this is all units business here. The potential fun can arise because capital W is the symbol for work, but capital W is the unit for power. Are you with me there? So it's not a big deal. You just have to be a little careful so that you don't get yourself confused. It's like I said, it's not super hard, but all right. Easy enough? You can multiply, you can divide. Life is good. Let me give you a ranking test to look at. Woohoo! All right. Jason and Brent. I'll read this to you because it's kind of a lot to see. Jason and Brent race up a hill that is 30 meters high. Jason takes a path that is 60 meters, while Brent uses a longer path that is 100 meters. It takes Jason 40 seconds, while Brent runs up his path in 30 seconds. They both start from rest at the same height and they both stop at the top. Also, they have the same weight. Okay, so far? Here they go, running up this funny looking hill. First question. Is the work that Jason does in going up the hill greater than, less than, or the same as the work that Brent does in going up the hill? So I'm gonna let you think about that for a minute and then we will discuss. There are a lot of numbers in there. So focus on what the question is asking. Why don't you have a conversation with your partners? See what they say. You guys have such quiet conversations. You should have a loud conversation.
I'd rather run up a hill with Jason than run. Why?
Do you like hills?
Yeah, I'm close today. I feel love hills, but.
What do you think? Does Jason do more, less, or the same amount of work as Brent does? Should we take some votes? Who are you guys voting for? More?
More, I guess, a little more.
What are you guys voting for? Or have you discussed? You guys don't look like you have an answer. We're still working. What do you guys come up with? More?
Probably more.
More? Team 4?
I'm honestly so confused.
Okay,
Just say more for the sake of.
okay. Convince me that that's the right answer now.
I thought it was actually.
Niamh doesn't look convinced herself. I'm not sure. I'm just watching her face, that's all. Not like trying to judge. Go, Haley.
The hill that Jason is going up is steeper, so it would require more work to get up it.
Okay. Okay. So steeper hill equals more work. So I'm just kind of trying to record stuff so we can have it. Go ahead.
Also, I kind of remember doing something like this in foundations where they say like ramps, like the longer it is, like the less work is required, it just takes longer. And then if you apply that to the formula, like you're extending the time if the path, like if you're taking a longer distance, which will be a smaller amount of work, and if you're doing it in a shorter amount of time,
Okay.
maybe.
Okay.
Unless I made that up.
No, I just was trying to, I realized that I wasn't writing anything down, so I'm just gonna keep listening. Is that okay? Niamh, what were you gonna say?
Since Brent is like going up the hill, but his side is like more,
Shallow, less steep.
yeah. So it's closer to being parallel.
Okay.
I guess you can say
Okay.
that.
Okay. Go.
So because they said that they have the same weight,
Uh-huh.
you can, that means they have the same mass, right?
Indeed,
So,
it does.
Let's say they're both like 50 kilograms.
Okay.
You can find the force by using m times speed. Can we do that in this case? Because
Sure.
they're not in free fall zone.
They're not in free fall, but you're just finding, so let's talk about the force, right? So, and this is something that we kind of talked about with Janelle and her pizza. So we could have Janelle on one of the other sides of the hill running up with a pizza. You with me there? Okay. So if she's running up with a pizza, or we started doing that one with the stairs yesterday, right? Which direction is she applying a force to the pizza? Or if you're running up the stairs, which way are you applying a force? Your legs start to hurt, right? Because you're pushing which way?
Forward.
Which way am I applying a force? I'm applying a force up, right? Does that make sense? The forward part that we talked about that a little bit, like the little hiccup at the beginning, hiccup at the end, right? To get us moving, okay? But really, the way you're applying a force is which way? Up, to climb up that hill, to climb up those stairs, to climb up the whatever. Is that okay? So the steepness of the hill means that the time may be different. And maybe we shouldn't have skipped question 4. Let's go back to question 4 real quick. That seems mean. Geez, Carbling. I knew I had to do question 4 for a reason. Who was moving a box? Magda was moving boxes because her family moved, right? Yeah, she was carrying a box up a hill, up a ramp. It was a 7-meter ramp. It was 30 degrees. Kibby was sitting over there. He was getting mad at you guys because you didn't remember your 30, 60, 90 triangles. You remember this?
No.
Yeah. You don't remember that he did this? We need to work on your short-term memory. He was. Yeah, he was berating you guys because you couldn't remember your 30, 60, 90 triangles. So he told you that this was 3.5.
Yeah.
Remember this? Yeah? Yeah?
How do you
And
know that?
Well, I see because it's half 7, but I don't remember anything to do with triangles. Like,
Well,
whatsoever.
friends. Okay, so then if you don't remember, then you just use you just use sine, right? The sine of 30 is equal to opposite, which is x over 7. Get out your calculators. Oh, friends, we got to do this. Come on now. You got this.
Isn't the other side like square root too?
Yeah, it's going to be 7 root 2. Yeah. It's an equilateral triangle.
I mean, yeah, you know, it's 3.5.
What'd you get?
3.5.
Oh my gosh!
I got 3.5.
Oh my gosh! It's like Kimmy knows how to do math. You guys know he was a math teacher before he became an administrator, right? Yeah.
What math class?
I mean, like, not here, obviously, but like, I don't know, he was a math teacher. He
Wasn't
just taught
it in
math.
at Jefferson?
I don't have any idea. All I know is that he was a math teacher. He's a math guy. All right, so 3.5. Yes, you okay?
Sure.
And we said that the mass of this thing, I think we got distracted. I'm going to tell you that the mass of the box is, I don't know, did somebody write it down? Write down the number. We'll say that it was 2.6 kilograms. Totally making that up. Totally making that up. So the work done. Nine 9.1, where are you getting that from?
Wait, maybe I did something wrong. I did 3.
I'm not saying you're wrong. I'm just asking.
I did 3.5 times 6.
What's the force he's applying, or she's applying?
Oh wait, I forgot to do the force. Wait, I did.
I got 9.1 as well.
So tell me about the force acting on the box. What a force is acting on the box. What you got? There's a force pushing down, Miss Carbling. It's the force of the earth on the box.
Okay.
And then you got the force of Magda on the box, right?
No, he's smart.
It's kind of embarrassing. Too bad I don't have the fart thing today. That would be funny right now.
Oh, he was not happy with
I know, right? Okay, so what's the force of the earth on the box? Can you find it?
Yeah, it was 25.51.
25-ish, right? Is that okay? So what's Magda have to apply a force up? How does it compare? It's got to be at least the same, right? Yeah. So the force is going to be 25 point whatever you just said? Did you say 25.51? Are you guys with me there? Does that make sense? What's the distance? 3.5?
89.29.
89.29 joules. Okay. Please hold. Okay, here we go. One more. Example 4B, here it comes. Magda's doing a different ramp. Here it is. It's a 22.8 or 22.9 degree ramp. It's 9 meters long. She's carrying the same box. How much work does she have to do? You guys understand the situation?
Yeah.
Okay. So she was going up this really steep ramp. She went up one ramp. Now she turns. She has to go up another ramp. It's a different steepness, also a different length. How much work does she have to do now?
I'm so confused with the 25.51.
Here?
Yeah.
It was 20, whatever that was. How? 2.6 times 9.8. Is that okay? All right.
You get 89.2.
There's
I don't
no
know.
any.
You should. You should.
I was like,
Yeah, because it's the same height, isn't it?
Yeah.
Same height, same work. I'm gonna write that down so we can remember that for tomorrow.
Oh, 'cause I was like, why is it the
After
exact same?
class, well, I have time to like I have questions on projects that I have to think right away. 'Cause
Hold
if I
on, just
went-
hold on one second.